Hey guys, welcome back. We are going to dive into some chemistry now. I know for a lot of you guys, chemistry is like a four-letter word. Nobody wants to do the chemistry. Maybe you're put off by chemistry in high school or something. But there is a lot of chemistry going on behind the scenes when it comes to the understanding of the biological system. And I promise you, I'm not going into any more detail than I absolutely need to go into so that we can understand the concepts in anatomy and physiology. And it'll be a cursory review of the basics of chemistry, but it's also very important that we understand those basics for this semester. And if you are going to take Anatomy and Physiology 2, which is the second part of this course in the next semester, then you'll still need to carry some of that knowledge over. Okay? Now, just to put this in perspective, we talked about the levels within the human body. We go from the chemistry level with atoms and molecules and stuff like that, and that's where we're going to start right now. Remember, we're going to have chemistry, we'll work our way up to a cell, we'll work our way up to tissues, right? We need to know that hierarchy. So here we are, we're at the lowest level. Obviously, it's a microscopic level. For a lot of you, seeing this periodic table of elements is probably the worst thing, and that's probably what scares you, right? We're not going to deal with all of the elements, all of these atoms that are the smallest units of matter that are going to represent each element. We're just looking at the elements, those elements that are prominent, that are they're more common in the biological systems. Okay? So let's get started with just the very basics, right? So if we boil it down, we could talk about individual elements, and the smallest unit that would be that we're going to talk about, that would be the composition of a unit within each element group, would be an atom. Okay? So we can talk about an atom within the group of carbon. Okay? Carbon is an element. The smallest unit within that group of elements would be an atom of carbon. Okay? Nitrogen is another element. The smallest unit of an atom there is going to be slightly different in size, but has a very similar structure. Okay? We could talk about sodium, something that is in your salt at home. Okay? Again, sodium is an element. The smallest unit that we're going to pay most attention to will be atoms within that group. Okay? Now, we could talk about within each atom the fact that there are subatomic particles called protons, neutrons, and electrons. Okay, so easy way to think about this. Think about the sun as a solar system, and we have planets that are going around the sun, right? Well, it's a similar situation here. If we look at the center of any atom, so here we have the center of an atom here for carbon, right? Center of an atom here for nitrogen, center of an atom here for sodium. This would be the nucleus of that atom. So it's almost like the sun is the nucleus of that particular solar system. Going around the nucleus, we have electrons. Okay? These electrons are always on the move. They're like the planets that are going around the sun. Okay? Now, what composes the nucleus are actually two subatomic particles, protons and neutrons. Now, the protons are always positive, and you might think kind of like that to remind you that it's positive. Proton starts with a P, and they are positively charged. Okay? So if you look at any one atom within the element carbon, we're going to find 6 protons in the center, partially composing that nucleus. We're also going to find some neutrons, but usually we don't talk a lot about the neutrons. A lot of times we're more concerned with the charge that the protons carry, which is a positive charge. So if there's 6 protons, there's a +6 charge going on the inside of this. So I'm just going to put 6, and I'll put a plus sign in front of that for carbon. Okay? Now, for a neutral atom, and when you look at the periodic table of elements, like that scary table I showed you just now, well, we actually talk about them as neutral, which means that they don't have a charge. Well, that must mean that for carbon to have a neutral charge, to not have any charge associated with it, it would have to have actually, we'll change it to a purple here, we would have to have 6 electrons. So 1, 2, 3, 4, 5, 6, rotating around the 6 protons, and altogether that would give you a neutral, a charge of 0, right? Now, look how these electrons are laid out. Some of these electrons, like these two, can be really close to the nucleus, and there's only room enough for 2 electrons in this first really close, we call it a shell for electrons, this first energy level. Okay? As we move away from that first energy level, we're going to find that there's more room for electrons. In fact, here with our carbon atom, we've got the 6 protons in the middle, and we've got 6 electrons, but only 2 can fit real close. To get our other 6 in there, we're going to have 4 in the next energy level. This is our neutral atom of carbon. Now, as we go through any of the other elements, we're going to find that it's a similar situation, right? So here we've got for nitrogen, it happens to have an atomic number of 7. So typically what they're doing is they're using the proton number to give you the atomic number. So nitrogen, having an atomic number of 7, tells us that it has a plus 7 charge in the middle with 7 protons, and it has around it, if it's a neutral atom, 1, 2, 3, 4, 5, 6, 7. Only 2 can be real close. We know that's the rule, but then more can fit in the next energy level. Now, as we go on further and further, we're going to find that the second, third, and so on, energy levels as we go away from the nucleus, are going to be able to hold more. And typically, there's this magic rule that they can hold up to 8 electrons. The first one can only hold 2, but then as we go out, we're going to find 8 can reside in the energy levels outside of that. So let's try this one. Here we've got sodium. Sodium has an atomic number of 11. That tells me there's 11 protons. Inside we have a charge of plus 11. There must be 7 electrons to make this neutral. Okay, so here you can see there are 2 real close. Okay, 2 from 11 means we need to find 9 more. We have 1, 2, 3, 4, 5, 6, 7, 8. Only 8 can fit in each energy level outside of that first one, right? So we don't have enough room for all of them in the second energy level. We have to go to a third energy level to have a neutral atom. Okay, so these atoms are the smallest unit of matter representing each element that we might want to talk about. Okay? Now, let's consider some of the ways that these atoms might interact with one another. Okay? So here we have, we're going to use red for this. Here we have on the left side, we have a sodium, and it's kind of weird. They have Na. You'd like to have an S or SO or something for this based on its name, but Na is the code for sodium. Okay? And we have chlorine atom over here. Okay? Now, let's go back to what we know about sodium. You may recall from the previous that sodium is going to have a plus 11. It has 11 protons, atomic number of 11. We're going to need to find 11 electrons. So here they are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, only 8 can fit in that, and we have our 11th one right here. Okay, there's our neutral atom of sodium. Okay, now let's consider chlorine atom. Okay, so happens that, so let's switch to green here for our protons, that this atom has 17 protons, an atomic number of 17. Now we have to find 17 electrons, right? Okay, well, we can only fit 2 real close, so 1, 2. That leaves 15, right? All right, 8 of those 15 can fit in the second energy level. So 1, 2, that's our octet rule, right? Octet for 8. 4, 5, 6, 7, 8. All right, that makes 10. Now we have 7 left. So we count them 1, 2, 3, 4, 5, 6, 7. Well, we only need one more, right? So put a little question mark here. We only need one more right here to make this an octet, 8 electrons in that particular outer shell. Now, the general rule of thumb is, even though these two atoms are neutral, that is not what makes an atom, quote, happy. Okay? For an atom to be the happiest, let's just say, this sodium atom, which has 1 electron in the outer shell, well, it doesn't have the 8 that it needs, right? So the easiest way to have 8 in the outer shell for sodium to make this sodium atom happy, it would just as soon lose that electron. This would leave these 8 that are in the second level, right? And that would satisfy the octet rule. Now for chloride, to gain an electron right here, right? So we'll give it an electron right there, would make this outer shell 8. It would satisfy the octet rule on that particular atom. And so quite often, 2 atoms like this will interact with one another, one losing an electron, another gaining an electron, but both atoms are happier in this way, and these 2 atoms reside next to one another in a fairly stable interaction. An ionic bond, we call that. Okay? And so here down at the bottom, we have something that is called sodium, okay, chloride, right? Looks like a 3rd grader wrote that using my cursor, right? But sodium chloride is just table salt, okay? This is called an ionic bond. In so doing, we have formed an ion on both sides of this bond, okay? On this side, our sodium lost an electron. That means it's going to be a positive charge of 1. Right? It lost a negative charge, so now it's going to be a +1 because it has 1 more proton than electron. Over here on this side, for our chloride ion, it's going to have gained an electron. It has 1 more electron than proton, so it's going to be chloride ion. These are both ions because they have charge. And if the ion has a positive charge, like sodium does, we're going to call it a cation. Okay? Now the key here is the T has a plus sign in it, right? If you look at that T, it looks like a plus sign. That'll remind you that cations are positive. Anions would be negative, right? So we have these ionic bonds, table salt, some of the minerals that are in your multivitamins. A lot of these are there in a salt kind of form, which is going to have an ionic bond involved. So in this case, one atom, the chlorine atom, totally stole an electron, right? And the sodium lost that electron. So one gained, one lost. We've got our ions making an ionic bond. All right, now let's consider a situation where two atoms don't actually completely steal electrons from one another. They may not have that kind of pull, like the sun holds the electrons, holds the solar system together, right? There's this gravitational pull towards the sun when it comes to those planets. Well, here we have the nucleus and a certain amount of pull for those electrons that are moving always around that nucleus, okay? So let's consider an oxygen molecule here, okay? Here we have an interaction between two atoms. It so happens, if we actually go in here, we'd find that the oxygen atom actually has 1, 2, 3, 4, 5, 6, 7, 8 for an atomic number. It has a +8 in the middle. And we find 8 electrons, 2 real close. 1, 2, 3, 4, 5, 6. It needs 2 more electrons to make that oxygen atom happy. And we have the similar situation over here. We have 8 protons, that's its atomic number, and we have 1, 2, 3, 4, 5, 6, 7, 8 electrons. 2 more electrons would make that atom happy. What these two particular atoms do, however, is they do not actually have the pull to completely steal an electron from the other atom. These two oxygen atoms end up sharing the electrons with one another. Now, this is almost like a tug of war. Imagine you and a twin who has the same strength warring over these electrons. They're pulling these electrons because there's a gravitational pull, right? Or you can also think of it like I've got a couple of ping pong balls and you've got a couple of ping pong balls, and what we do is we kind of share them equally. We keep tossing them back and forth to one another equally. There's no time where one of us has all 4 or more than 2, right? There's this constant sharing going on, okay? We would say that this oxygen molecule has a shared set of electrons, okay? There's a sharing going on, we call that covalent bond. And the fact that it would be an even sharing, where these electrons are not one on one side towards one atom or another any more of the time, we call it a non-polar covalent bond, okay? What this also tells me is that this oxygen molecule is not going to have the electrons more of the time. So it's not going to have more negative charge on one side or the other. So when we talk about an oxygen molecule, so another way of writing something about an oxygen molecule, you would have O for the oxygen and 2 for 2 oxygen atoms interacting in this molecule. Or sometimes they'll write it like this. They'll say, okay, one oxygen molecule has 2 sets of electrons being shared with another oxygen atom, okay? So each of these lines would represent the sharing of 2 electrons. 1 electron from each atom being shared, okay? Okay, so let's now take this other molecule over in the bottom right of your slide here. This is a water molecule, and again we see an oxygen atom here, and it, just like any oxygen atom, is going to have 8 protons in the nucleus, atomic number of 8, and we count electrons. So 1, 2, 3, 4, 5, 6, 7, 8. Problem is, those yellow electrons that oxygen originally owns as a neutral atom, they don't fulfill the octet rule, right? We need 8 electrons in the outer shell. Well, it so happens that hydrogen has 1 electron to share for each hydrogen molecule, a hydrogen atom. So here you can see that hydrogen shared its atom on each side, and we can see that this gave oxygen its octet rule. Hydrogen satisfies the rule for its inner shell because only 2 can fit there, and we have now an unequal sharing of electrons. It so happens that oxygen has a much greater pull for electrons, and so you will see that the electrons are going to be pulled towards that oxygen more of the time. Okay? What this means is there is going to be a partial charge, and that's what this symbol means, of negativity towards the oxygen atom. So in this case, you think about it like I'm playing catch with a couple balls with 2 different people, and at some point I just hold on to those balls, right? I'm going to have those associated with me more of the time because I'm being a hog for the balls that I'm holding on to, and they're not going to be with you as long, right? So I'm going to have more negative charge because the electrons are negative, and these hydrogens are going to have less negative charge. We would see a positive charge associated with that side of this water molecule. This is like a tug of war between the 2 little guys and this big guy here, this oxygen atom. So we have an unequal sharing. It's still a sharing of electrons going on, covalent, but unequal means polar. There's going to be this charged situation because there's a polar covalent, uneven sharing of those electrons. Okay? All right, the last thing I want to deal with here to just kind of round out the different kinds of bonds we're going to run into, let's consider this water molecule that we just talked about, right? We said that there's this polar covalent situation. Sometimes they'll draw it like this. So I have my oxygen atom, I have a bond on either side with a hydrogen over here, okay? Again, this represents the sharing of 1, 2 electrons, 1, 2 electrons for each covalent bond. And we're going to have more of a positive charge on the hydrogen side and a more negative charge on the oxygen side because the electrons are there more of the time. So here we have it, right? Oxygen is in red here. We have a negative charge. Hydrogens are positively charged. Now, if we pour a bunch of water molecules, right, into a glass of water, well, they're all going to kind of interact with one another, right? And what we might suspect would happen is that negative charges, like we see associated with this oxygen down here, okay, so this is a negative charge, might be a bit attracted to the positive charge of another water molecule. So we would have an oxygen molecule atom kind of getting up real close to the hydrogen atom of another water molecule. And you see this dashed line here between these 2 atoms. This would represent a hydrogen bond. Okay? So this is telling us that because of a polar covalent sharing, right? Polar covalent bond between this guy that's a hog for electrons, the oxygen, and the small atom of hydrogen, because of this charge that's formed, because of polar covalent interaction, we have what are called hydrogen bonds forming in between the water molecules. Now this is a weak bond. Hydrogen bonds are weak, but if we consider a glass of water, well, it would have millions of water molecules in there, and when you think about the millions of hydrogen bond interactions that exist, it really makes for quite a considerable interaction occurring between these water molecules. Okay, so if you look at water, a bead of water on the countertop, right? Maybe you spilled a little water and it's just kind of sitting there. It's kind of like a little bead on the counter. Versus in chemistry lab, if you spill a little bit of ethanol, an alcohol, right, on the counter, or I'm sure none of you have considered what vodka, I'm sure none of you know what vodka looks like on your countertop at home. But if you spill an alcohol like vodka, which has 40% alcohol in there, on the counter, it's going to look very different because these water molecules are not interacting in such a strong fashion when you look at alcohol that's been dropped on that counter. So the very reason that you have this beaded up look to some water on the countertop is because of these hydrogen bonds. Okay? Okay, we're going to leave it at that for now, and then we'll dive into some biochemistry, define that, and look at what some of these molecules do when they're combined, right? When we combine salts and things like that in the water that makes up most of our body. Okay?